So, yesterday we talked about the fact that in science in general, whether it's chemistry, physics, biology, it is the desire of the scientists to discover relationships, discover the relationship between variables. I've tried to get across to you in the past couple of days that when it comes to talking about a gas, there are four very important variables: the volume, the pressure, the temperature, and the amount of gas that we're dealing with, the amount of gas that we're studying, how much is in there. And in order to look at the relationships between these various variables, we need to keep other variables constant. And we did a very quick simulation of an experiment, but I have the actual apparatus here, where we chose a certain amount of gas. So I draw some gas into the syringe. I then connect that gas to a pressure meter, all right, a barometer of some sort. And I can then now manipulate the volume of the gas and take a look at how the pressure changes, all right? We've kept the amount of gas constant. Once I sealed it off, no gas is allowed to enter or exit. And we're keeping the temperature constant. This apparatus is functioning in the room at room temperature, and therefore we can look at the relationship between volume and pressure. And if I had to make you write this as a formal write-up, and we could have, it actually is something that we could do easily as a formal write-up. We could talk about, right, the purpose would be, what is the relationship between pressure and volume with the temperature constant and the amount of gas constant. You could have done a hypothesis. I think it's going to be a linear direct. I think it's going to be an inverse, whatever. We could have done our variables, right? What were we manipulating? We were manipulating the volume. What were we observing? We were observing the pressure. So here we've got independent and dependent. What were the controls? Temperature and the amount of gas, right? We could have did the whole 9 yards, all right? But no need to. We've done that quite a bit, and this was just one where we did it very quickly. And what did you find? What was your situation? Did you have the linear direct line, or did you have the inverse curve? Inverse curve, excellent. And really, as we were taking data, we should have been able to figure that out, because as I made the volume smaller, what did the pressure do? It got bigger. And when one variable gets smaller and the other variable gets bigger, here, I'll use my thumbs to help you out on this. That's an inverse relationship. Right? We're okay with that? Okay. So that shouldn't have been a surprise to you. Now, in university physics, you can have all kinds of different inverse relationships. Like I said, you could have y being proportional to the inverse of x. That's what we had. But you could have y being proportional to the inverse of the square of x. You could have y being proportional to the root of x, or sorry, the inverse of root of x. You can have y being proportional to the inverse of x to some fractional exponent, 3.5. There's all kinds of different relationships that exist out there in nature. And as the physicist / chemist, your job would be to determine what that relationship is. To keep things kind of simple in this little introductory application of this to our sciences, to gases, I told you it's either going to be linear, direct, nice and easy, or it's going to be straight up inverse 1 over x. And you guys determined that it was inverse. That's correct. Very nice. So let's write a little bit of this down as an official note, just so that we've got it in our notes. The relationship between the volume and pressure of a gas. We got that title down? Excellent. And you don't have to draw this or write this. Don't write anything. This is just showing what you obtained, all right? Now, yesterday I talked a little bit very quick. Actually, I didn't talk about it much. I very quickly said about how you could, actually with this class I didn't. This class I didn't go into this detail. Let me just add on a little bit here. If you have an inverse relationship, it looks like that, right? And that's what you saw yesterday. But if you have an inverse square relationship, it looks like that. The numbers are different and they'll be shifted, but it won't be obvious just by looking at the graph which one it is. If you've got an inverse root relationship, it looks like that. Yeah, they all look the same. That's the point of me writing that down. If you have any inverse relationship, it's got that funny curve to it. So it's very difficult sometimes to know which one it is. And I very quickly went over this yesterday and said, you don't need to worry about this. Remember I said, don't worry about graphing the 1 over pressure, right? I said, don't worry about that. That's the way you test to figure out which one it is. If you think that it's an 1 over x, then the trick you use is to take all of your x numbers and do a calculation to figure out what the actual 1 over x number would be. So if I had an x number of something like 2, then my 1 over x value would be 0.5, because it would be 1 over 2. All right? And if I had a number of 3, my 1 over x value would be 0.33, right? And if you graph, then, instead of x and y, and you graph y versus the numbers of 1 over x, if you graph that and you get a straight line, then what that means is, because remember, this says that y is directly proportional to x. But notice what I have on the x-axis. Now I have 1 over x. So what this means is y is directly proportional to 1 over x, which is what we thought it was. This is called curve straightening. Curve straightening is a method that you can use to test whether your guess was right. You guess at this, you calculate this, you graph that, and if you get it straight, your guess was right. You know it was 1 over x. If I didn't get a straight line here, I could either get a line that looks like this or looks like this. I could even get another one that looks like this. If it's not straight, then you've guessed incorrectly. In the 12U physics, we'll give you one that's one of these, all right? And we'll make you guess, not straight, guess again, not straight, guess again. And then if you find that when you calculate x and 1 over the root of x, and you make a graph of 1 over the root of x, and it's straight, finally, I got it. I figured it out. Now, when I was a student, we did that. We graphed it, not straight. Rats. Pick another one, do another calculation, graph it, not straight. 3 or 4 graphs, going crazy, straight. Whew. Nowadays, you can put those numbers into a computer, and you can say to the computer program like Excel or even a special graphical analysis program, you can ask it, could you tell me what you think the exponent is? Bam! Gives it to you. Done. You could check it to make it straight, but the computer is really good at doing what it does. So you can have the computer just tell you, by the way, that's an inverse relationship. You can even say, could you please give me the equation for this line? No problem. Give you the equation. Done. Right? So nowadays, you put it in the computer, and bang, it'll analyze that curve for you every time. This is why we wanted you to make the volume of gas 1 over pressure, because we wanted you to see that it was a straight line, and that then would say, yes, your guess of the inverse relationship is correct. All right. We didn't do that. Not a big deal. Okay. So, Boyles Law. All right. Let's write some stuff about Boyles Law here. And actually, you're going to write that whole thing. So you saw graphically that the pressure is inversely proportional to the volume of the gas. Which, the variable in which I change doesn't matter. If I change one of the variables, the other variable automatically changes with that inverse relationship. So I always have to have a fixed amount of gas. I always have to have trapped gas. And it always has to be at a constant temperature in order for this to be true. As soon as you start varying those other things, there's other things that come into play. But that is always the case. In our experiment, as I make the volume smaller, the pressure goes up. All right? Now, if I could somehow manipulate pressure, I could do that. If I could somehow make the pressure get bigger, I could see then what happens to the volume. But it's very difficult for me to manipulate pressure in this way, right? I can easily manipulate volume, but I can't just manipulate pressure. I'd actually have to, if I wanted to manipulate the pressure inside that thing, I'd actually have to have a way to vary the atmospheric pressure, all right? I could change it in a couple of ways. My silly example of when you squeeze on a balloon to increase the pressure, the volume of the balloon goes down. That's a very difficult thing to do, really, in practicality. If I attempt to squeeze on that balloon, the balloon's going to try to squeeze through my fingers, and bang, I'm going to end up breaking the balloon. The reason I end up breaking the balloon is because I'm actually increasing the pressure in there, right? The way to change the pressure is a difficult thing. What I actually need is my little vacuum pump, and Mr. Petrus borrowed it, and I don't have it back. I might grab it in a minute. What I can do is I can take this balloon and I can put it underneath this jar, and if I connect this hose to a vacuum pump to suck the air out of the space, I can manipulate the pressure in that space. Very hard thing to do just in my hands. As you get doing some practice problems, I'll get the vacuum pump and I'll show you that particular situation. Another way that I could kind of affect the pressure, this is a tricky thing, because if I squeeze that down, am I changing the volume or am I changing the pressure? I'm actually doing a little bit of both. I'm actually squeezing it down to make the volume smaller, but I'm also increasing the pressure inside there. What I'm showing you here is that I've got some liquid here that doesn't compress. So if I put a pressure on this, you'll notice what I'm automatically doing is I'm making that bubble smaller. As I increase the pressure on this plunger, the bubble decreases in size. So by changing the pressure, I can change the size of that bubble. Now there you can see it's getting smaller, but that's not really an exciting thing. That's like when I just squeeze on it when I don't have anything in it. If I get rid of some of this water, maybe I can get rid of some of this water here. Let's get rid of some of the water. Let's just get a tiny little bubble. Let's close that off there. And let's get the bubble to sit on the side here. Now here you can see the bubble kind of sitting on the side. If I give this a squeeze, you'll hopefully notice that the bubble truly gets smaller. Whoop! Where'd the bubble go? I squeezed it so small it disappeared. Wow. That was magic. What happened there is the air bubble squeezed through here on me. That's not a very good syringe. What's the matter?
You're making me nervous, Tom.
That would be funny, don't you think? That'd be hilarious. Okay, let's see if I can get that bubble come back. That was fun. Okay, let's see if we can draw that bubble back in there. There we go. Little bubble in there. All right. There it is. Now I think if I squeeze it like this, then it's going to squeeze back out on me. Oh, there it is again. So I got to keep it away from the plunger. Okay, I don't know why I'm coming back here to get the air. Let's just get air bubble. Well, let's keep that air bubble in the corner there now. And if I squeeze it, I hopefully you can see it get really tiny. Oh, I'm now squeezing water right out of the syringe. That is, what kind of a garbage syringe is this? Look at this action. Oh, look at the power right there. That's garbage. Absolute garbage. I'm just squeezing the water right out of it. Well, that was no fun. I was hoping you'd see the bubble get a little smaller. All right. I'll get the vacuum pump in a moment, and we'll take a look at that. A couple of more things. There's our inverse relationship, right? And I can move the V to this side, and then I'm going to have P times V is equal to some constant, K. We called it K yesterday, all right? That means the pressure times the volume in an isolated gas is always constant. So if the pressure goes up, the volume has to go down so that P times V always remains the same. All right? So that's what they mean by the constant. We can put that, let's not worry about that. We can put that together in Boyles Law formula, which you've already written down. Hopefully that's on your lab somewhere. Some of you might have put the V's first, but it doesn't matter. Typically, we write it simply as P1V1 equals P2V2. Okay? Now, we've seen a calculation very similar to this. Pressure and concentration of an aqueous solution is a very similar property. When you put the pressure on something and you squeeze a gas together, what you're doing is you're squeezing the particles together closer. You're literally making it more concentrated. There's more molecules in each volume. So the equation for dilution, and please don't write this down, but does anybody remember our dilution equation? What is the dilution equation for concentrations and volumes? Pause for recall. Dilution equation, yep. Yep. And you'll notice this says P1V1 equals P2V2. Concentration in an aqueous solution is very much related to pressure. We're just squeezing together the particles, or we're drawing them out and making them more separated. Just like in a concentrated solution, when we evaporate the liquid, we're having the particles that are dissolved come closer together, and when we add water, we're causing those particles to separate out. Okay, let's get rid of this. Now, just like in our concentration dilution equation, again, the units don't matter. Does anybody remember what was the most important thing about the units? Somebody have a hand up there? No? What's the most important thing about the units when we use that dilution equation? Didn't matter what units we used, but they had to be the same because they had to cancel out. So in this equation, because it's a ratio, pressure could be in kilopascals, but pressure could also be in atmospheres. Doesn't matter. They could be in torr, they could be in psi, etc. They can be any pressure unit. Same with the volume. We're not locked into any volume units here. They can be liters, they can be milliliters, they could be meters cubed, again, etc. The main thing is that the units must be the same. Be the same. Okay? So at this point, we'll do some example problems. I'll give you a little practice sheet. I'll let you work for a little bit, and then we'll work on the next two variables, volume and temperature. Those are the next ones we want to look at. Okay. Yep, don't mind that. You can write that question down. As I stated, this is just like the problems that we have dealt with concentration. It doesn't matter which one you designate as 1 or as 2, as long as they're together. So you can go ahead and solve this one without me. I don't even really need to wait. I've got a balloon. It's got a volume of 22.4 liters at 273 Kelvin and 1 atmosphere. What will the new volume be if the pressure is doubled to 2 atmospheres and the temperature remains constant? So the temperature data, I don't even need. It's constant. I'm looking at the relationship between this volume and this pressure. I'm now changing the pressure. I want to know what the new volume is. So again, as long as they're together, I'm looking at the data. I've got a P1. Sorry, I should have started with V. There's the V1. V1, 22.4 liters. And the pressure that goes with that is 1 atmosphere. I want to know what the new volume is. V2, question mark. And the second pressure, P2, is 2 atmospheres. Now we should be able to think this through actually quite logically. I'm doubling the pressure. I'm making the pressure 2 times as big. If the relationship is simply an inverse, what's the new volume have to be? Yep, half of the old volume. Because if you double one variable, then because of the inverse relationship, double inverse is 1 over 2. It should be half the volume. And that's another way to think of inverse relationships. They really are that straightforward. If I triple the pressure, what happens to the volume? What's it going to be? If I triple the pressure, what would the volume become? What's the inverse of triple? 1/3, right? If I made the pressure become 1/2, what if I made the pressure get smaller by 1/2 of its value? What would happen to the volume? It would be doubled because it's an inverse relationship, all right? So keep that in mind. That's always a quick check. Sometimes, though, I don't give you nice questions where it's not exactly doubled or exactly, it might be like 2.735 or something like that, so you got to do some math. But keep that in mind. It's an inverse relationship. Okay, so P1, V1 equals P2, V2. Put your numbers in, 1.00 atmospheres. V1, 22.4 liters. Hopefully some of you are ahead of me. You shouldn't have to be waiting for me to fill this in. P2 is 2.00 atmospheres, and V2 is what we're looking for. We're dividing off the 2. Oh, the horizontal line stinks. You know that. 2.00 atmospheres is being divided off. There we go. 2.00 atmospheres divided off. That is gone. That is gone. 22.4 divided by 2. What is that? 11.2 liters. V2. All right. So that illustrates a couple of things, how we use the equation, and the fact that you can use some logical sense on this stuff as well if you've got some easy, numbers to work with. We doubled the pressure, we have half the volume. And let's do one more. I think one more. Yep. No need to write down that homework. Actually, I'll just take it off the slide because the homework is on the sheet. Even the textbook questions are written on that sheet that I gave you. Great word there that you're coming across right now. Isothermally. What a great word. Isothermic. We've encountered iso in this course. Hopefully I've impressed on you what it means. We encountered it in the term isotope. What did isotope mean? Same, the tope part, what was it? Come from maps, like topographical maps. Meant same place, right? Remember the isotopes were the atoms that had the same number of protons. They were always found in the same place. You're going to need to know that for an upcoming exam. Anyway, what would isothermally mean? Yep. Yeah, same temperature. So if we have the volume change under isothermal conditions, it means the volume has changed, but the temperature has stayed the same. And we need that to be the case, because when we study our variables, Boyles Law is true when temperature is constant and the number of moles is constant, then we can see that relationship. Hopefully you're way out ahead of me doing the calculations. I've got, I'm going from 10 to 30, and the initial pressure was. So 10 and my pressure go together. V1 is 10 liters, and that goes along with the initial pressure, 1140 millimeters of mercury. V2 is 30 liters, and I want to know what P2 is. Again, I'm going quickly because I'm hoping you're out in front of me here. P1 V1 equals P2 V2. Whoops, that's a horrendous V. 1140 millimeters mercury. Volume 1.0 liters. P2 is what we want. 30 liters. Divide off the 30 liters. Divide off the 30 liters. Notice the units, sorry, I didn't want to get rid of the 10. The unit liters cancel. That's why the units have to be the same. The 30s also cancel on that side. P2, what do we got? Yep. 380 80. 380 millimeters mercury, which we know is that funny barometer thing, right? Nothing fancy here. Make sure the units are the same. You've got that equation to work on. What you're going to work on now for about 10 or 15 is the top section of that sheet that I just gave you, all right? And I just want to point out a couple of things. Notice it says in number 1 in that grid for the second pressure in the second example, notice it just says standard pressure. What are you going to put in there? What is standard pressure? Not standard ambient pressure, but just standard pressure. The S of the STP. Sorry, the P of the STP. The pressure of the standard temperature and pressure. What is that value? What's standard pressure? Yep. Yeah, 101.3. So be careful. Those terms come into play now. If I say standard ambient pressure, 100. Notice that the unit on the left is kilopascals, so I'm going to want 101.3 kilopascals. But if the unit on the left was PSI, I'd have to put my 14.7 PSI. All right? So be aware of those terms. If you encounter them, they're telling you what the pressure or the temperature is. Okay? All right. Like I said, 10 or 15 to work on this.